The third and final form of the independent variable probability, Poisson probability. Here's an example. Jonah is desperate for some money to buy a Sprite. He takes his metal detector to the beach and starts scanning. The International Association of Beachcombers reports that on average there is 2.65 pieces of metal of worth per square kilometer of sand. Given that, what's the probability that Jonah will find 8 pieces if he scans 2 square kilometers? So here's a classic example, which is a Poisson probability. Poisson probability is used for infrequent events when the probability for success is given per unit. Like in this case, this is 2.65 per square kilometer. Right? That's our degree of success. And so this is kind of a generic per unit because, in this case, it's per square kilometer, which is area. You could have, success of, fishing is a classic example where you catch a certain number of fish on average per hour. So that's per time. Or you could do it per volume. There's all kinds of different, units that you could use. So in this case, there's 2.65 pieces of metal of worth per square kilometer. Right? So that's kind of, it's like a rate of probability. Now, kind of like geometric probability, there's a formula. And like geometric probability, we are not going to derive it. This actually tends to be a more complicated formula than the other two, has pieces that you might not have seen for a little while. So let me just show it to you. And there it is. Now, before you freak out, don't worry about it. There's all kinds of crazy stuff here. We'll go through it. It isn't as bad as it looks. So first of all, this E. Well, that's not a variable. That's the number E. That's Euler's number, which is about 2.718, right? It's that number. You know that pi is approximately equal to 3.14. Pi never changes. So in fact, E never changes either. And its value is approximately 2.718. It's irrational, so like pi, it keeps going. There's a lot of cool stuff about actually the number E, which is also called the natural logarithmic number. Beyond the scope of this video and this course, I hope you actually already came across that in maybe Algebra 2. It's on your calculator, 2.718. It's a static number. Now this lambda, all right, this takes a little bit more discussion. It's a little wordy, but lambda is the mean number of successes per unit of interest. In this case, what is our unit of interest? Now, if we go back to the question, right, our per unit is square kilometers, except that how many square kilometers does Jonah search or scan? Right? We have 2. Right? He searches, starts searching, piece of metal, down here. He searches 2 square kilometers. So our lambda has to be based on 2 square kilometers. That's the unit of interest. Interest is 2 kilometers. So what we have is 2.65, and what we have to do is multiply by 2 because 2.65 is for 1 square kilometer. Our unit of interest is 2 square kilometers. So this becomes 5.3 pieces per 2 square kilometers. So that's all that lambda is. So you just have to be careful because usually, like it is here, Averages are given per single unit, but oftentimes in these kind of questions, your unit of interest is multiple units, like 2 square kilometers. Then the last thing is R, which is actually just like we have seen before. It's our outcome of interest, which in this case, of course, is 8. We're interested in the probability of Jonah finding 8 pieces of metal. And so all we need to do is the probability of finding 8 pieces of metal, e raised to the negative. A lot of people will forget the negative sign, and that causes problems, i.e. the wrong answer, times positive 5.3 raised to the 8th, all over 8 factorial. If you plug that into your calculator, you end up with 0.077, or he has a little under 8% chance of finding 8 pieces of metal of worth if he scans 2 kilometers. Now, again, we have our calculator. We have Poisson PDF, which can, oops, I didn't want it in there. So going back, we have Poisson PDF. All right, the syntax for this, I'll put up on the board. The calculator needs 2 pieces of information, lambda and r. So in this case, we'll put in our 5.3, comma, and our outcome of interest, which in this case is 8. And there's our 0.077. You can put that up on the board too. Of course, the next obvious question is, show the probability distribution. I'm going to use the calculator because it's far easier doing it that way. So here I have my stat lists again, of course. L1 is outcomes of interest. What's the probability of Jonah finding 1 piece of metal, or 2 pieces of metal, or 3 pieces of metal? 7. I go up to 10. Again, somewhat arbitrary. Because is there an upper limit? Could he find 1,000,000 pieces of metal? I suppose so. It's unlikely, but it could happen. Again, there's no upper limit. We do have to be a little bit careful here, because is 0 a possibility? Could he find no pieces of metal? And the answer is he could find no pieces of metal, so we do need 0. We don't want to exclude that. Could he find -1 pieces of metal? No, that doesn't make too much sense. So we can come in here, and we can just use our Poisson PDF in our L2. This is our 5.3. Our outcome of interest is now L1. And there we are. All right, we can kind of scan down. Looks like this is the biggest number. Thinking about in terms of graphing what our y max is going to have to be. So I could go to Windows, go down to y max 0.3. Let's take a look. That's very nice. And of course it will continue. I only did the stat list up to 10. If I could do the stat list up to 20 if I wanted to. Of course, it's going to get smaller and smaller. We can hit our trace. It's always good to see what the maximum is. So looks like the maximum probability is going to be finding 5 pieces, and the probability is about 17.4% chance of finding 5 pieces. And of course we can go over to 8, and there's our 0.077. or 7.7% chance of finding 8 pieces of metal. Here I've copied the information and the distribution. Now, interesting question might be, how many pieces of metal could Jenna expect to find? We're now talking about expected value, which is mu, which for Poisson distributions is very easy. Expected value is the same as lambda. And the variation of the probability distribution is the square root of lambda. So in this case, this would be 5.3, or, because it's a discrete variable, really, he would expect to see or find 5 pieces of metal. And the measure of variation about that expected value, 2.3. So, 68% chance of, getting up to, 7, or maybe, down to 3. It gives you a little sense of variation. An interesting issue is what happens if you use 1 var stats to try and get your expected value and standard deviation? Well, you end up getting 5.17 about, and this is 2.13. They're different. Why are they different? Well, they're different because this isn't the whole sample space. We can't actually get the whole sample space because it's infinite. Right? 11 is a possible outcome, 12, 100 is a possible outcome. So these are only approximate, which is why, in this case, really we should use the formulas.